We are Group 2, and our presentation is on electrochemistry. Sir Humphrey Davy of London was the first to challenge Volta's rule that only the contact of metals was what powered the battery. Davy added that chemical reactions are also needed. Davy had a student named Michael Faraday, whose laws are still used today that implied the rules to correctly predict the results of the current passing through a chemical compound. Electrochemistry is the chemistry that happens in a battery. Electrochemistry focuses on the chemical change that creates movement in electrons. Electric current is what's used to jumpstart chemical reactions, called electrolysis. Electricity is generated by the moving of electrons, formed from movement from one electron to another. This process is called oxidation reduction or the redox reaction. During a redox reaction, the oxidation of the elements involved are changed.
Hello, my name is Alfredo Rodriguez, and I'll be discussing how electrochemistry is used outside the laboratory by talking about batteries. Batteries are one of the greatest innovations that have revolutionized the world. They power small appliances like your controllers, flashlights, calculators, laptops, phones, and even your earbuds. Batteries can also power tools to create and construct, power and move vehicles, and even power a house. Thanks to electrochemistry, we are able to supply and power most of our electronic devices and other things that require power. And that is how electrochemistry is used outside the laboratory.
Hello, everybody. My name is Antonio Chavez, and I'll be going over the requirements for experiments 1, 2, and 3. For experiment 1, we need red cabbage, a petri dish, 9-volt battery, and alligator wires, as well as graphite, pencil lead. For experiment 2, we'll need alligator wires, potato, zinc nails, copper penny, and an LED light. And lastly, for experiment 3, we will need zinc washers, vinegar, salt, tape, an LED light, and pennies. For experiment 1, we will need to get a red cabbage indicator solution. We do this by putting the red cabbage into a boiling pot of water. After a short amount of time, we would get our red cabbage solution. Once we get our solution, we will then put some of it into a petri dish, roughly about halfway. Once we get our petri dish settled, we would then get our 9-volt battery and our 2 alligator clip wires. We would connect one end of the wire to the negative side of the battery, and on the other wire, we'll get the one end and put it onto the positive side. We would then get 2 pieces of lead from a pencil and stick one piece on the negative and one piece on the positive side of the alligator clips. Once we're done with that, we would then stick both pieces of lead inside of the solution. On one side, we will see a green color, and on the other side, we'll see a pink color. Green is negative, and pink is positive. For experiment 2, we need to get a potato and cut it into 3 parts. Once we cut them into 3 parts, we will then place pennies on the left side of each potato slice, and on the right side, we will place our zinc nails. Once we're done with that, we would then connect our wires. Our wires will connect from penny to nail and continue on to each potato slice. Once we're done with that, we will then connect our negative and positive side of the wire to the LED electrodes, one on the left and one on the right. We should see the light turn on because it produces enough voltage. For experiment 3, we would need to get a piece of cardboard and a penny. We would then cut penny-sized holes into the cardboard. Once we're done with that, we will stick it into a vinegar and salt solution. Once the cardboard is done soaking up the solution, we will then stack the cardboard from penny zinc washer to cardboard and then repeat that process. Once we're done with that process, we would then tape the LED electrodes to each side of the stack of pennies, washer, and cardboard piece. Once that is complete, we should see the light turn on because it should produce enough voltage for the light to turn on.
Hello, my name is Karina Lopez, and today I'm going to be going over the calculations portion of the presentation. As the first part of this lab, we actually didn't really have to calculate anything other than just to find the chemical equations. that are listed in part 1 right here. So we just had to find the dissociation of sodium chloride, and then the half reaction of the anode and the half reaction of the cathode, which are going to come in handy later on. Also for part 3, part 3 is where we actually had to calculate some stuff, but it's pretty easy, simple math. But these reactions are also going to come in handy for part 3. The main thing to remember about anodes and cathodes is just that anodes are going to have their electrons on the right side, and they will usually be an acid, and their color would be an acid-like color, so like pink, like in our lab. And then for the cathode, their electrons will be on the left side, and the cathodes are usually a base, and their colors are blue-greenish colors. And I'm not going to go too in detail into these chemical equations because it's just something to show for later reference, or future reference. But yes, so now we just have to find the standard electron reduction of our anode and our cathode. So for part 3, our anode was the zinc ion, and then for the cathode, it was the copper ion. So I looked at, or we all looked at the standard reduction potentials table, and that is where we found those values. So the value for the zinc ion or the anode is negative 0.76, and the value for the cathode is positive 0.339. You can also use positive 0.34. Both of these are used. It just depends on what table you are using, because there's different sites that have different tables. And usually the one that's more positive is more likely to be reduced. Now, these standard electron reduction values are actually very important for the standard cell potential. So all you have to do for the standard cell potential is subtract the cathode and the anode, and you basically get your answer. So we subtracted the 0.339 minus negative 0.76, which gave us 1.099 electron volts. From here, we use that number to help us determine the delta G. So we use the formula NF and then your E cell, which right now your N stands for your 2 electrons, your F stands for Faraday's constant, and then your E cell is just what you calculated right above it. So you do the math, and then from there you can use that number to help you determine if your delta G is spontaneous or non-spontaneous. If your delta G is positive, then the reaction is non-spontaneous. If it is negative, then your reaction will be spontaneous.
In these 3 experiments, we could observe and understand how the movement of electrons produce electricity. A galvanic or voltaic cell is a spontaneous process which produces electrical energy from the chemical energy in the redox reaction. The solution losing electrons is being oxidized, the anode, while the solution gaining electrons is being reduced, cathode. And an electrolytic cell is a non-spontaneous reaction that needs an outside power source to bring chemical changes. Anode here is a positive polarity, while the cathode is a negative polarity, the reverse of the galvanic cell. Since these types of cells require a specific setup, it was essential for the experiments to be set up in a correct way for the LED light to emit. A few issues that could be problematic were making sure the alligator clips were on the correct side of the battery, making sure the nails were positioned across the copper penny for the current to be created, and last but not least, layering the battery we created correctly with the filter cardboard piece in between. Though they took a few tries, we managed to conduct electricity in all 3 experiments, certifying the process of electrochemistry.